Great to be here. I'm Julian Togelius, and I just really minutes ago finished putting together these slides, which are called Increasing Generality and Reinforcement Learning through Procedural Content Generation, or Have Fun Trying, which may or may not be a reference to a 50 Cent album. It's really just like presentations of 4 papers wrapped into some overall questions. Before we get going, who am I? What do I do? I'm at New York University, as Robert said, and I'm also working with a startup called modl.ai. So at least 2 hats, but I have a very big hat, so I can fit 2 hats. I may be most well known for working with procedural content generations in games, coming up with new algorithms for generating levels, maps, quests, stories, characters, rocks at some point. And the other big thing that people may know of me for is creating a bunch of game-based AI benchmarks. Like I've created AI benchmarks based on various car racing games, Super Mario Bros, this general video game AI benchmark we've seen before, and been involved in creation of a bunch more. And the idea is that games can be really useful for testing the capabilities of various algorithms and AI architectures. One that I'm quite excited about that I was involved in, which is a PCG-based AI benchmark, is Obstacle Tower, for those of you who have heard about it. I've also been working on AI-assisted game design tools and dabbled in a bunch of other things like game design research, imitating human playing styles, and modeling and predicting player experience, and so on. All right, so one question that I have been thinking about for a long time is, can we learn a policy that plays more than one game? Because we've been spending so much time on building or learning or some very combination thereof, bots or agents that play one game, and then they're like, you can't make your best StarCraft bot play Super Mario Bros. Because not only would it be bad at it, it wouldn't even understand what it's seeing. It's like, the inputs and outputs don't match. And even if you made a match, it would just be gibberish to it. So basically, how do you come up with something that has more than one competence? And to a large extent, I've had to scale back my ambition to how do we come up with an agent that, even if it only plays one game, at least plays this game under different settings and different levels, maybe with different screen sizes or whatever. Because it turns out that almost everything we build is extremely narrow and specific. Variations of these questions have been studied under the term transfer learning, where you rephrase it as basically, if you learn to play one game, how can you build on that to learn to play another game? These are not exactly the same questions, but strongly related and with strong bearing on each other. Oh, by the way, when I say game, just think about it as environment or problem or whatever you want to say. Some people would prefer to talk about so-called more generally about like things that are not games as problems or environments. I tend to see it as like, why not see everything as a game? That just makes more sense logically. Some games are just more amenable to experimentation than others. One big problem is that transfer learning with deep reinforcement learning does not work well. Training an agent on one problem and then testing it on another generally does not work at all. Training it on one problem and then keeping training it on another problem to sort of generalize the performance generally does not work very well. There's a little evidence that you can build on what you learned in solving one problem when it comes to learning to solve another. And also even less evidence that you can do it without destroying what you already learned in terms of solving the first problem. Another way of looking at this is in terms of overfitting. We all know about overfitting from supervised learning. If you look at overfitting in terms of reinforcement learning, you can see it as Overfitting is when you are overfit to play a single game, or so to solve a single problem, or even a single instance of that problem, or single level of a game. And it could be even more specific, a single instance of that problem with a single starting condition, and with a single screen size, and a single color palette, and whatever. As you may or may not know, if you just take a standard, deep RL approach and train an agent to play a given Atari game, then it cannot handle in general that you move it a few pixels to the left or right, that you sort of, if you go into memory and change the position of the ball in Pong, so it's just something completely different. Maybe in Pong you could, but in many games you couldn't. It's extremely specific. So I would like to argue that much of what's happening here is overfitting, but why is it overfitting, and how is it overfitting? What can we do about it? Continuing the analogy to supervised learning, overfitting means that you fit the data well. If you overfit, you sort of fit the data too well, you include the noise, it doesn't generalize. If you underfit, you don't fit well enough. And this is like, there is thousands of papers about this, and there's whole fields of research in just how you do in just how you deal with this. Different forms of regularization. But so in supervised learning, generally things you can do, including getting more data to avoid overfitting, and the particular larger your model get, the more data you need. Keep separate training, validation, and testing sets, of course, and then stop training when validation error increases. Limiting model size is an old and good one that you, for example, you prune decision trees. There's pruning techniques in neural networks as well. And then there is various regularization methods. There's dropout. There is various sort of, downwards weight pressure on connection weights, and a zillion other things. But generally, very many of these approaches have to do with the amount of data compared to the size of the model. Now, from the perspective of supervised learning, what is done in most reinforcement learning is searching for a proper word here, but ridiculous. You're essentially training on your testing set. Some people might take issues with this characterization, but I think it is fair to say for most deep RL research that you are training on your testing set. Then exactly how much variation you would need to sort of not be training a testing set, that's up to discussion. I think it's bizarre, and we need to stop doing this. I'm not the only one who says this, of course. This is a pretty general sort of, insight that we need to move away from this. So let me throw out a couple of hypotheses. Why does deep RL overfit? So is this because we're training on a testing set? Is this because a training set is small and homogeneous? So if we're playing a game, we're playing the same level over and over, or the same 3 levels or something, or same 3 levels in the same sequence, for example. Is it because our models are too large? I mean, if you look at the amount of information you get strictly through the rewards in reinforcement learning, because we all know that rewards are sparse and there isn't that much information. That's basically a scalar every time. And you compare this with a number of parameters you have in a typical deep network that's used for deep RL. That comparison does not come out well. You generally do not seem to get enough information to set all the weights in this giant network. So that would, according to some theory, imply overfitting. Or is it because the input representation favors learning specific strategies? So your network and your learning method could have learned a more general strategy, but the way you're representing your input, it sort of makes it easier to just learn something that overfits. Or is it something else? Is it something with the algorithm? Something you can do there? I am not saying this is like an exhaustive set of different hypotheses, but these are some hypotheses that I consider reasonable, and conceivably several of them could be true at the same time. Okay, so on the menu today, that was a bit of like, a bit of like ideological sort of, setting the stage for what I'm talking about. So now I want to talk about 4 papers from the last 2 years. One where we try to generate levels, so to create more general deep RL agents. One that we try to generate very small networks to implement a policy. So we try to constrain the model size as a form of regularization. One where we create input representations that encourage learning more general policies. And finally, some ongoing work where we evolve maps that maximize diverse behaviors in single policies. So we try to say, okay, we're only going to find one policy, but how can we make this policy be able to manifest as many different behaviors as possible? And this will go from the work that this is roughly in chronological order, and to some extent building on each other. So the first work here, this is work was done mainly in my lab, except Nils, who was here visiting from Copenhagen. He is now at modl.ai, working for us, doing industry-focused stuff. But we call it Illuminating Generalization and Deep Reinforcement Learning through Procedural Level Generation. This was published at, I think, the NeurIPS DeepRL workshop 2 years ago, if I remember right. Or 3 years ago, maybe. Now I can't remember. No, 1 year ago, maybe. Yeah, well, whatever. So we created this thing called the General Video Game Playing Competition. This is something that I've been working on for a long time. It's a competition and an associated software framework and description language where you can create games that are roughly of the complexity you will see from late 70s, early 80s games, the things you would find on a Commodore 64. And we have a description language where you describe what goes into the game, how these things interact, and so on. So you can very easily, with changing a few lines, have different games. And we have variations of, like you see here, Pac-Man, Frogger, the Overworld, The Legend of Zelda, or like inspired by, and a couple of other things. We have, I think, 160, 170 games in this framework. And the idea is that you can very, very quickly create new games and create new levels for these games by human or by machine. And the end goal, to some extent, is that you could sort of combine game generation with agent generation and generate a set of games to be played by a set of agents and so on. All of these games are playable by humans as well, to different extents. The UI isn't really great, and the game feel is somewhat lacking, but you can play these games. For example, Pac-Man is not a good version of Pac-Man, but it's playable. And in the original version, we have a number of different tracks here. In the original version of this, you submit controllers written in Java, because that's what we used for writing the main framework. And these models get a forward model, and they can do planning of different kinds. We also have a learning track where you submit RL agents. They do not get a forward model, they get training time. The learning track has never worked that well for various computational infrastructure reasons, I would say, and that we just didn't have the effort to put into this. But the idea is that every time the competition runs, we score the submitted agents on a number of unseen games. So you don't have, you have never seen the games you're going to play when you start playing them. And they're written in the video game description language, this is an example of a game. This is, you have a sprite set at the top, which is sort of the ontology. These are the things that exist in the world. You have a goal, which is a door, and the image is goal. You have several types of movable things. You have avatars, no keys, with keys, and so on. You have level mapping, and the level mapping, I see now I do not have a mouse pointer, so I cannot point to things, sorry. The level mapping maps the separate level files, as you see here to the right, to the game ontology. And then you have the interaction set, which are the core rules of the game. For example, when anything that moves interacts with a wall, then it stops. If an agent which has a key interacts with the goal, then the goal disappears and the agents get 1 point, and so on. And then a termination set, which decides when you win and when you lose the game. We've had quite a lot of fun implementing a bunch of different games in this framework. Some of them sort of interesting, many of them just like poking at sort of extreme conditions of learning. So here's an example of the overworld of Zelda, inspired by it, played by a human. This was, by the way, the game you just saw, described in that set of sort of in the description in the previous slide. This is played by a random agent. Not good. And this is played by Monte Carlo tree search, or technically expect max open loop tree search. And here we see like the issues with like having rollers that go as far as you can to find the door. Currently the guy is lost, none of the rollers find the door, then there he found it. And you can, here's a version of Space Invaders. This is MCTS playing this and playing it fairly well. For some reason, starting with destroying his own defenses, but then it gets very good at shooting the aliens. And this is, of course, not very interesting in itself. The interesting part is that it's exactly the same agent with no changes. This is a version of Boulder Dash, the classic 80s game, played by the same agent. And this turns out this is extremely hard because there's a lot of long-term planning and Twitch-based play you need to do to play this game well. So we do not have any agent that reliably solves the first level of this game, which is kind of interesting. So there are some hard challenges in here. All right, back to where we were. Okay, so we decided to try to train agents for these games. No forward model, a standard A to C algorithm, and a deep net architecture, which is very similar to the, well, basically the same, but adjusted for different input size with the classic sort of DeepMind sort of DRL networks or architecture. Pre-convolutional layers, one fully connected. And then the output is interpreted as like up, left, right, down, nothing, and the fire button. So here we have, oh, why is this not playing? Oh, now it is playing. And now I have a mouse pointer. Okay, here we have an agent that's trained on a given level. And sorry for the low resolution. We had to do this for computational reasons. The agent is being tested on the same level it was trained on, and as you can see, it plays well. No surprises here. This is what we would expect. This is what deep reinforcement learning is supposed to do. So we built a number of level generators for each of our games. We had Solar Fox, Zelda, as you saw before, Frogs, which is a version of Frogger, and Boulder Dash, the very hard one. And they provide endless supplies of levels. These are hand-coded level generators. We could have built level generators of many kinds before. You could possibly use something like GANs. We have a separate set of work that we're trying to use something. We've been using GANs to generate these things in different ways, but they tend to not preserve playability constraints very well. So we tried a number of other sort of network architectures for generating this, but these are just hand-coded methods. So this is basically a handmade, these are handmade generators. And what we did, so you can see here, this is difficulties between 0 and 1 for these games. So in Zelda, difficulty 0 is really simple. There are almost no walls to get stuck on. There are no enemies. You can run and get the key, and then you can run to the door. And even if you just took random actions, you would eventually make that. And then as difficulty ramps up, walls get longer and more connected. It gets more maze-like, and there are more enemies. Frogs or Frogger, in difficulty 0, you have this you have a tiny screen or tiny playing field, and you have no sort of obstacles moving through the level, and you just have to go to the exit. And at difficulty 1, you have a lot of different obstacles. Same thing, similar thing with Boulder-Dash there. It gets more puzzle-like and more sort of complex the higher you crank up the difficulty. So now we trained on level 1, and we're testing these tiny procedural generated levels. So you look at this level. This is like a travesty of a level. You have the agent to the top, to the bottom right, and then you have a key and a door. And if you just jammed the directional keys randomly, you would win. Turns out that an agent trained on level 1 does not necessarily win this level, because it hasn't seen it before. It doesn't know what to do, which is kind of hilarious given how brutally simple it is. But this is just like, if you want an existence proof of the overfitting that goes on, here is one. You couldn't possibly make a simpler level, and yet it is not being won. Now, what we did then was that we started by training using procedural generated levels. So every episode we gave the we trained on new levels, because the level generator was that fast. So overfitting to a specific level would be impossible. I mean, you never see the same level more than once. And as the level, oh, that's a missing sentence there, or like an incomplete sentence. As the an agent learns to play these levels, the difficulty of the generator is increased. So we generate more and more complex levels as it gets better. I think we increase it as soon as it wins more than half of episodes with a given difficulty. So we call this progressive procedural content generation. It's nothing political here. It's just that the difficulty progresses. And as you can see, in all cases, we do manage to increase difficulty, but to different extents. Much quicker so in Frogger than in Boulder-Dash, for example. And we have a pretty janky sort of noisy line in Solo Frogs. So how well does it do? Well, better than the ones that are trained on fixed levels, but not so well as we would have hoped. So here we have a guy that managed to almost find the door. It found the enemies and managed to dispose of them. And now it is like confused because there's this tiny bit of wall in between itself and the door. And oh my God, what am I going to do with this? I'm stuck. This is so hard. Which is kind of laughable, of course. This is not what you'd expect should happen. Let's see, I have a bunch of examples here, I think. Probably staying too long on this one, which is not going to be. Yeah, okay. A couple of other ones. Won it. So they are pretty good. They are much better than they were initially. They handle enemies in lots of different places, but they can still get stuck on, like, inconsequential pieces of geometry. What did we do? What happened here? Oh, some of them it just wins immediately. But here it's stuck again. Almost finishing it and then stuck on like nothing. Oh no, it won it. Interesting. Yeah. So we are making progress. We are achieving some kind of generality, but we are still it's still mysteriously unable to do what seems to be very, very simple spatial reasoning about things we find. Here is trained on this progressive PCG and tested on a human-made level. I can't remember if it actually does this. Yeah, no. I don't think it actually solves the human-made level, or maybe occasionally it does. Which is, of course, like a disappointment. But it seems that there is still some, you could characterize it as there's still some overfitting going on, but not to a single level, but to a shape of generated levels, a type of generated levels. Yeah, let's solve this one. I guess not. Too long since I watched these videos. I have too many of these. Right. So we have a mixed success here, basically. It does get better, and it does have a reasonable solution percentage of the hard level generators, but that doesn't mean it necessarily solves the human-made ones. Which made us ask, are the generated levels like the designed ones? And we tried to sort of figure this out by doing projections of various kinds into a space and try to place the generated ones next to the designed ones. And it turns out that yes, as far as we can tell, they are. With every metric we can find, they're quite similar. But still, we're not managing to solve the human-made ones. So the results are mixed. We do get better, not for all the games. It doesn't necessarily sort of, we don't get the same amount of success in progressive PCG setting, but but they have, but in some games it does very well, and it doesn't necessarily generalize to human-made ones. All right, so yeah, and we overfit but to class of environments rather than single environments. And another takeaway from this is that learning navigation in 2D environments seems very hard, and possibly the way we're presenting the inputs is what makes it hard. And this is something we get back to in the third paper, where we're sort of looking at input representation and see how that biases the agent to learn to sort of navigate in 2D environments or to not do it. Because one suspicion we had after this set of experiment was that maybe 3 convolutional layers and 1 fully connected layers cannot learn to navigate in a 2D environment from a third-person perspective. Maybe there's kind of maybe the kind of machinery that we needed to, for example, search for the path from a key to a door is not possible in a feed-forward network of that size or that depth. I still think that this is true, and we're going to see what happens in the third paper. In the meantime, we look at another thing, what we call playing Atari with 6 neurons. This is a collaboration with Giuseppe Cucco and Philippe Cudrier-Marot in Switzerland, in Fribourg. This is mainly Giuseppe's work with my input of various kinds. Ideological input. I don't know why I want to use that word, but yeah, a bunch of technical stuff as well. So going back to the other hypothesis that the models are huge, these networks are really giant, and in particular in relation to the number of rewards we get. We don't seem to have enough information to be able to train these networks well, which would seem to mean that they would overfit. You can make you can compare to a big network, you can compare to a decision tree, an unproven decision tree, which overfits and is pretty bad. What if we separate the visual processing from the policy part? So we have a separate visual processors, and then we train a tiny network that that implements the policy. Would this overfit less? So we came up with what we call the increasing dictionary vector quantizer to find the centroids, the representative frames in the input stream, and then use sparse coding to create the features that can be delivered to the neural net. So the idea here is that instead of feeding the raw pixels into the neural net, as you train, whenever you sort of find an input scene that is sufficiently different to what you have already, you add this as a new centroid, sort of a new archetype, and then you have a sparse coding that represents how far away you are from the different centroids, and use that as an input to the neural net. Just as a note here, you could have used many other different sort of feature representations. I did some work with autoencoders as input preprocessors, which I haven't mentioned here. But yeah, once you have this thing, you train a very small, fully connected recurrent net, which you do with a natural evolution strategy. You could have used something else. You could have used any kind of policy gradient or any kind of evolutionary algorithm, I believe. But this is what we used here. So the architecture here, so you have a compressor that I can't see this because I don't have a mouse. Okay, I can't see the full thing here, but basically it selects frames and trains the compressor by finding the centroids, returns a sparse code of this into the controller. Controller selects action environment, and the environment delivers observations to the compressor. The training happens only on the controller space, so it trains a pretty small network. They're pretty small. It's pretty few parameters that are being set. The compressor is not directly connected to the evolutionary algorithm at all in this case. So when I say the centroids, what does it mean in this case? So this is one of the centroids in the game Qbert, where you basically jump up and down a big pyramid and try to color all the different sort of floor tiles, while not getting eaten by monsters and stuff like this. So here you have like the first centroid and a number of differences, like particular sort of differences we see from the first centroids, which are also in there. You can see it as the other features are residuals, so lit cubes, avatar, enemies, and so on. And here we seem to have a video fail. This shouldn't look like this. Not sure why it looks like this. I think some kind of video codec or something has been updating. I hate it when they update, but anyway, maybe you can see a little. Oh wow! Now it looks right. You see Qbert going up and down this level and playing fairly well. So for this game, this is one of the games where we managed to get not the level of the best networks, but levels very comparable to human play and comparable to anything else we found with evolution, or that anyone had, usually better than what the other people had found with evolution. And comparable to sort of like a naive attempt at playing these games with a DRL. Let's see if this is working. Nope, this is not working. Oh. Okay, this is some kind of video codec thing again. Sorry about this. Anyway, so what we managed to do here is that, yeah, it's broadly comparable to the OpenAI evolution strategy experiments, but with several orders of magnitude smaller network. So it basically has 6 neurons instead of like many hundreds, and like a few hundred weights compared to tens of thousands. This works. This is one of these papers that had this interesting history. It was rejected by one or two of these big conferences, and then it was accepted by AMAS, which is also a pretty big agent-based conference, and won a Best Paper Award, which is like says something about the sort of stochasticity of papers and paper acceptances. But what we found, you can learn policies of basically the same quality using orders of magnitude smaller networks if you just factor out all the visual processing, so you only do policy. One obvious question is, how well does this generalize to other kinds of games? We think it will generalize to almost anything that does not involve scrolling backgrounds. The particular kind of preprocessor here will absolutely not handle scrolling backgrounds, and will probably not handle most first-person games, but would probably handle anything non-scrolling third person. Now, as to the main hypothesis, would these tiny networks generalize better? We didn't test this because we only use this with Atari, and Atari is very hard, almost impossible, to test different levels of the same game, because you can't go in and poke the memory representation in RAM in any kind of simple way. Maybe they would, or maybe the overfitting would be in the visual preprocessor, which would be interesting in itself. The actual experimental setup of these experiments is a little bit specific, using Ruby and other things, and so we sort of retired this code base, but someone, maybe us, maybe someone else, should at some point redo this in something that would interface better to modern sort of workflows. Right. Yeah, this should have been in the beginning, basically. Like, is what's being learned in these larger networks more like a lookup table? I do think that sometimes it is more like a lookup table, but yeah. Right, I see I should move on given the time I have. So on to the third paper here. Rotation, translation, and cropping for zero-shot generalization. This is coming straight out of my lab. And this is pretty much directly inspired by the work we did in the first paper. So after those results we got in the first paper, we spent some time trying to think about what could we do to make this generalize better using the same GVGI setting. And one idea we had was that we should be able to characterize the sort of failure cases, the ones where the deep network would not do well, and maybe try to learn from, try to create some kind of like ensemble method that learned from the research-based methods to sort of to perform more generally. This didn't work. We spent a lot of time working on this, but it got nowhere. And then at some point where we sort of, had one of these sessions where we're like, getting real tired of just like slamming our head into the wall, and it needed some kind of new, fresh take on this. I thought, but well, if the problem is that if you can't learn to navigate using a fixed third-person perspective, why not make it more like a first-person perspective, and see if that will help it generalize better. So this is the previous work, the first paper, and if you notice that the papers, we've done some work with VisDoom, so you have a first person or egocentric view in Doom, and it seems that they generalize fairly well to, in particular, various mazes. And when you think about it, it's fairly easy to learn like a policy that can run around well in a maze, because you can just learn a few simple sort of rules, and then you look at the walls you're faced with, and you can learn local rules for how to deal with walls, for example, instead of having to learn something very global, which helps you sort of actually navigate a maze. Think about the ancient Greek myth of Theseus going through the labyrinth to find a minotaur. He had a super simple local rule of basically just like laying out his thread and not going back on his thread, basically. So maybe that is the key. Maybe navigation is just much simpler in first-person view. So what we did here is that we took GPGI and first we rotated it so that the avatar is always facing forward. We replaced the avatar with a pink object so that we wouldn't be able to see which way it's facing. So you see basically here, you turn the avatar and what happens is the screen turns. There you go. And the avatar is always at the center of the observation. So we have to pad the screen a lot. So you, or you could pad a screen, or you could basically just see part of a screen. And then you crop it. So you limit the view to the local area. And you get this view here. You have the pink object in the middle, and you see a 5x5 area around the agent. And you're always facing upwards. You're always in the center. So you're sort of getting rid of a lot of navigation problems. So we trained this, and what happened was that you train this on a few levels, and we get, let me see here. So the way to read this table is that cropping, translation, rotation, 0, 0, 0 means the original case, that you can't actually sort of, that you're not cropping, not translating, not rotating, and 1, 1, 1 means the all of them applied. And we didn't necessarily get better at the training case, but not much worse either. But we got a lot better on the testing case in many of these cases. So if you take Zelda, generalization performance, while still not good, was up from 0.4% to 22%. If we did all three of these. And the simple Zelda, which is a simplified version of it, we had excellent generalization performance. We had really good ones with all cropping and translation rotation, but for some reason, even better when you only rotated. We don't know why. And for SolarFox, which makes sense because it's less direction-based, cropping and translating in itself increased generalization from 49% to 90%. So Boulder Dash almost never does well, but even there we could see a statistically significant improvement in generalization performance. So I think this is the clearest result I have here. This pretty much without qualifications just seems to work. Cropping, translating, rotating to turn it from a third-person perspective problem to a first-person perspective, it actually means you remove a lot of information. You give the agent less information you would otherwise. But what I think happens, or part of what happens, is that you take away the easy solution of overfitting to a very specific maze, and you force it to learn something more generalizable, because you can no longer overfit easily. Yeah, these are tables saying the same thing, basically. And here's an example. You're seeing here the same agent level being played, to the left without cropping, translation, rotation, and to the right with all of these on. And it may look very confusing to a human, but at what you see on the right, but clearly not to a neural network. Right. Yeah, we have a hypothesis that especially looking at Boulder Dash, if you need global information, especially the cropping is bad for you. But the rotation and translation is clearly good and would work across the board. So this is the last thing I'm going to say a few words again, and then I really got to finish because we're really over time. Is ongoing work together with Joseph Suarez and Philip Isola at MIT, formerly of OpenAI, and it's me and my student Sam Earl. And we're looking at multiple competencies. So basically, can you create a single policy that can exhibit many different behaviors? And how do you do this? Can you find levels or maps that make the agent learn this? So we're using neural MMO, a multi-agent RL environment built by Joseph Suarez. And it's an attempt to make a much more complex sort of multi-agent RL environment, which is very much inspired by various MMOs. So the agents must maintain food and water levels, maintain health, they can attack each other, they have different kinds of attack, very much like a role-playing game. And you provide food and water when you're killed, basically drop loot. Harvesting wood provides food consumption bonus. You can cook. Mining ore provides attack bonus. Smithing, and the different sort of, you can be differently good at different sort of attacks. You have skill levels for all of these things, and these skill levels can be leveled up or down independently. So what happens here is that agents trying to survive using some policy gradient in an inner loop, while a population of maps are evolved to elicit maximally diverse behavior from the agent in the outer loop. Training agent environments that present a variety of niches, each demanding different survival strategies, should make agents more adaptable to new challenges. The thinking here is that we want to find, so one important thing to remember here is that all of the agents share the same network weights. Not the same network activations, but they technically have the same policy. And what we want them to do is this policy to be as flexible as possible, so the same agent can adapt to too many things as possible as we can. And therefore, we have the global measure of how diverse behaviors the policy can exhibit. And there's usually like a few dozens of agents in the game at the same time. Again, sharing the policy, but exhibiting different behaviors. We spend a lot of time working on different behavioral diversity measures. It turns out that this is this is not easy at all. How do you measure how different how diverse behaviors are among a population? We looked at discrete entropy measures, pairwise distance, just like looking at distance between all in behavior space among all agents, differential entropy, calculating the convex hull of behaviors, and so on. And they all have different pros and cons. We're not going to go into here. What we see here is like we see niche formations in good examples. So these are maps evolved using a direct representation, so basically tile flipping. So we're evolving straight on like a matrix and describing all the tails. And here we see some parts we find harvesting and combat being expressed more, and some other parts we see fishing and gathering being expressed more. And we can look at like the map, the heat map of where visited, where wood cutting is happening, where fishing is happening, etc. This is a video. Does it play? Oh, it plays. It's great. I got this last, Sam sent me this yesterday. So I'm not sure I can comment intelligibly on this video. But you're seeing relatively different behavior expressed by the agent. The agents are these like, things on an evolved map. Here we have an evolved map with more visibly different areas. We're trying a number of different policies here, and you see some of these are cutting wood and so on. And I think you see a bunch of fights going on here. This guy just died, and so on. And yet another evolved one. Right, I'm definitely over time, so I'm going to finish the talk now, and we can discuss.